Hey guys, this is a video about the 9 common techniques for rewriting integrands. In this video we're going to look at using trigonometric identities to rewrite integrands so that our basic rules apply, and we're also going to do what's called multiplying and dividing by the Pythagorean conjugate. Whenever you multiply by the conjugate, we're tending to use trig identities anyway, so it made sense to do both of those in the same video. So here's a simple example of one where you might use trig identities. Maybe you just have the integral of 5 to the x minus x cubed plus, say 2 over x squared plus tangent squared of 4x. Okay, obviously trig identities are not relevant to these 3 terms, but trig identities are relevant to this one. If I look at my basic rules on my sheet, I've got rules for the antiderivative of sine and the antiderivative of cosine. I've got a rule for the antiderivative of secant times tangent, secant squared, cosecant times cotangent, cosecant squared. I've got lots of different rules. I've got one for tangent, one for cotangent, but I don't have anything for tangent squared. So we're going to use trig identities here. I also wanted to review some of the other basic rules and algebraic techniques, so I just added these few terms at the beginning. Now this one is a basic rule that people often forget. So here's the rule. It turns out that if you take the antiderivative of a to the x, that's just an exponential function. It's a different base than the base e. It turns out you always get the same exponential function divided by the natural log of the base. So whatever that number is, you're dividing by natural log of that number and then adding c. Remember from Calc 1, when you took the derivative, you were always multiplying by natural log of a. When you take the antiderivative of a to the x, you're dividing by natural log of a. So here a is 5, and we're just going to get 5 to the x, all divided by natural log of 5. And this one is a simple power rule. So I bring my constant coefficient down, -1, then I add 1 to the exponent, and I divide by the new exponent. And dividing by 4 is the same as multiplying by 1/4. Now this one requires a little bit of algebraic manipulation first. Notice that I've got an x squared in the denominator. If that was just an x, I would think of that as a 2 times a 1 over x, so that I'd get a natural log out of it. But that exponent's not a 1, it's a 2. Since the exponent is not a 1, we need to bring that up to the numerator and use the power rule. So first thing I'm going to do is factor out the constant. There's a 2 there and an implied 1 in the denominator, so there's a constant 2, factor that out, and then I will antidifferentiate this x squared that's in the denominator. If I bring that up to the numerator, that's going to be x to the -2. Now I'm ready to do a power rule for that. And then for this last one, this is where I'm going to use my trig identities. Now you may have forgotten, it's been a little while since trig, but we've got a couple of Pythagorean identities, actually 3 Pythagorean identities. Sine squared plus cosine squared of the same angle is equal to 1. If I take this and I divide it by sine squared divided by sine squared is 1. Cosine squared over sine squared, cosine over sine is cotangent. When I square them both, that's going to be cotangent squared. And then 1 over sine squared is cosecant squared. You need to know those 6 reciprocal identities, how cotangent, cosecant, and secant are related to sine, cosine, and tangent. And they're very important and they come up often in this class. So you might need to go back and review those. But sine squared plus cosine squared, if the angles are the same, that's 1. If I divide by sine squared, I get this identity. If I take the same original Pythagorean identity and I divide everything by cosine squared, sine squared over cosine squared is tangent squared. Cosine squared over itself is 1, and 1 over cosine squared is secant squared. Now this is helpful because I don't have a rule for tangent squared, but I do have a rule for secant squared, and I do have a rule for 1. So I can take this third identity and solve it for tangent squared by subtracting 1 from both sides. And I can take the antiderivative of that instead. So tangent squared is secant squared of my angle, which happens to be 4x in this case, minus 1. And that's what I'm antidifferentiating rather than tangent. So I'm going to substitute that in down here. And now I've got a rule for that and a rule for that. We'll be good to go. All right. So I'm going to bring this term down. I've already done it. This one. And then this one I'm using the power rule. So I add 1 to the exponent. Negative 2 plus 1 is negative 1. And then I divide by the new exponent. Now the antiderivative of secant squared is tangent squared. If that's a kx inside, if it's not just an x but a kx, put your kx back inside. If I was taking the derivative, I'd have to multiply by a 4 by the chain rule. When I'm taking the antiderivative, I have to divide by the 4. And the antiderivative of 1 with respect to x is x. Don't forget your plus c. That's our answer, it's just not simplified. So I'll write it a little prettier. That's a minus 2. That x to the negative 1 is going to be an x in the denominator. Alright, so there we are. So that's using trig identities just for that piece, and then we reviewed some other basic rules. Now here's another one where trig identities would come in handy. First, I'm going to FOIL. I notice I've got a binomial squared. U sub doesn't work, so I'm going to expand the binomial squared, so that, like our first technique. Just an example of that. Secant squared times secant squared, or excuse me, secant times secant is secant squared. Secant times negative tangent is negative secant tangent. Don't forget your variables, x. There's another secant of x, tangent of x, so I've got 2 of them. And last times last is tangent squared. Oh, I guess this is exactly the same identity that I used on the last one. So I'll have to do another example as well. Here I've got a rule for this. That's antiderivative of secant squared is tangent. I've got a rule for that. The antiderivative of secant times tangent is secant, but I don't have one for tangent squared. But, as we just saw in the last example, because of our Pythagorean identity, tangent squared plus 1 is secant squared, so tangent squared is secant squared minus 1. So this simplifies. I've got that secant squared in that one, so I've got 2 of them. And the minus 1 is still there. We can antidifferentiate. Antiderivative of secant squared is tangent. Antiderivative of secant times tangent is secant. And don't forget, the antiderivative of 1 is just that constant times your variable, which happens to be x plus c. Alright. So those are trig identities. Here's another one that's similar, where you might do the same thing. I've got sine of 3x plus cosine of 3x quantity squared. Without that 2, that's just a basic rule with a kx substitution for the sine and the cosine. But with that 2, I'm going to have to write it twice in FOIL, so I expand to the binomial. It's like our first technique. Oops, I don't know why I wrote secant. And then FOIL. First times first is sine squared, angle stays the same. Outer times outer is sine of 3x times cosine of 3x. Inner times inner is the same, so I've got 2 of those. Last times last is cosine squared of 3x. Do you see the identity? Well, there are 2 of them that we're going to use this time. Sine squared of an angle plus cosine squared of the same angle is 1. It's our first Pythagorean identity. It comes from applying the Pythagorean theorem to a point on the unit circle. So this squared plus this squared is 1, so I can combine these 2 guys. Together, they make 1. So I've got a 1 there. Now for this other guy, this guy, that term, we could do a u sub, and you could let u equal sine of 3x, or you could do a u sub and you could let u equal cosine of 3x. But this one's even easier if you remember a trig identity. And this is one that comes up a couple of times in this course. You're never going to be required to memorize it. It's on the sheet with trig identities that you use for trigonometric substitution and trigonometric integrals in a couple of sections. So you're going to have this identity written on a sheet for your test. But it comes up so often that I've memorized it. Turns out that sine of 2 times an angle is 2 times the sine of that angle times the cosine of that angle. And that's a very nice identity. I've got 2 of those right here. I've got 2 sine of an angle times cosine of an angle. Turns out that that is sine of twice the angle. My angle was originally 3x, so when I double it, my angle is going to be 6x. So that's that. This is sine of 6x. And now I can just do the kx substitution for that. Antiderivative of 1 is just x. Antiderivative of sine is negative cosine. Of my angle, since I had a 6x inside, if I differentiated, I'd have to multiply by a 6. If I'm anti-differentiating, I have to divide by the 6. Don't forget to add c. And that's that. Okay. Now let's talk about multiplying and dividing by the conjugate. Now I tend to use multiplying and dividing by the conjugate when I see something that looks like this. I'm just going to use x instead of a constant times x. Now notice I've got a 1 plus cosine of x, and we have those 3 Pythagorean identities we discussed. We discussed sine squared plus cosine squared is 1. Tangent squared plus 1 is secant squared. And cotangent squared plus 1 is cosecant squared. And they're all related to each other. These 2 guys can be derived by dividing this one by sine squared or cosine squared. Now the conjugate, when we say multiplying by the the Pythagorean conjugate of a plus b is a minus b, and vice versa. That's what we mean when we say conjugate. So if I have a 1 plus cosine of x in the denominator, its conjugate is 1 minus cosine of x. If I've got a 1 minus sine of x in the denominator, it's going to stay exactly the same, but I'll just change the sign sign there. It's going to be 1 plus sine of x. What about tan x plus secant of x? Its conjugate is tangent of x minus secant of x. Here's a conjugate that you may have seen in Calc 1. If I've got 1 plus square root of x, the conjugate of that is 1 minus square root of x. Or if I see 2 minus the square root of x squared minus 4, careful here, leave that sign alone, you're going to change that sign. That's 2 minus that whole thing. So you're thinking of that as the sign that needs to change. Doesn't seem very nice telling it needs to change. This one needs to change, that one doesn't. It's totally fine. So that's its conjugate. When we are using this technique for antiderivatives, it's usually when the integrand involves something like this. This is what we're going to see over and over again, where we will multiply by the conjugate. And if one of these happened to be under a square root, let's say you had this in your expression, well then its conjugate is going to be exactly the same, but make sure that one has a square root too. So that the square root of a times the square root of b is the square root of a times b. You could write it all under one square root. Now, here's the property of the conjugate. If I take a minus b and I multiply by a plus b, first times first is a squared, outer times outer is ab, inner times inner is minus ab, and last times last is negative b squared. So these two middle terms are always going to be the same in magnitude, but with opposite signs. So you're always going to get a squared minus b squared when you multiply by the conjugate. And that means we're going to get a lot of ones, basically. We're going to get a lot of expressions. If you multiply 1 plus cosine by 1 minus cosine, you're going to get 1 minus sine squared. And because of that 1 minus sine squared, we're going to be able to use this Pythagorean identity to rewrite it. Something similar happens here. Something similar happens here. So that's why we do this. When I multiply these two guys together, it's going to simplify to something that can be simplified further with these. That's why it's also in the Trig Identities section. So let's just see it in action. We're going to need these three identities, and we're also going to need our reciprocal identities from Trig, and we'll review those a bit as well. So I'm going to take my 3 over 1 plus cosine of x. Guess I should go through my list. First, notice that basic rules do not apply. You've got a plus sign here. You cannot separate the denominator. U sub doesn't work because the derivative of cosine has a negative sign in it. It has a sine of x in it, and there's no sine of x in the numerator. If there was a sine of x, I could do the u sub, but there's no sine of x, so I've got to do something else. So I go to my 9 techniques, and the most appropriate one is multiplying by the conjugate. So I look at that denominator, and I come up with its conjugate. That's a 1 plus cosine. Its conjugate is a 1 minus cosine. Multiply the numerator and denominator by the conjugate, and you get that. Now, the numerator I'm pretty much going to leave alone, but the denominator I am going to simplify. I'm going to FOIL, because my goal is to rewrite it using my trig identities from up here. 1 times 1 is 1. I get minus cosine plus cosine. Those reduce, so those are gone. And cosine times negative cosine is negative cosine squared. So we're here. Now, according to this, if I'm solving for sine squared, 1 minus cosine squared is sine squared. If I subtract that cosine squared from both sides, I get sine squared by itself. So this denominator is really a sine squared. Okay, so we're here now. I factored out my 3 as well. And then you say to yourself, okay, now what? Don't multiply by the conjugate again. If you do, you're just going to end up back where you started. It's not going to help you. Can we do a u sub here? Not really. We could let u equal sine. Its derivative would be cosine, but we couldn't do anything about the 1. So we'd have a problem. We could do a u sub for just this term. Hey, we could separate the 2 terms. So that's one possibility. So first, after multiplying by the conjugate, we're going to separate the numerator. So you have 1 over this minus cosine of x over that. And then simplify. 1 over sine squared. If you don't remember, that's cosecant squared. Make sure you review those identities. Now this can be solved with a u sub, but it's easier if you can remember those Pythagorean identities. So not Pythagorean identities, excuse me, reciprocal identities. So here are the reciprocal identities that come up over and over again in our course. Cosecant of an angle is 1 over sine of that angle. And secant of some angle is 1 over cosine of that angle. And cotangent is the reciprocal of tangent. And of course, reciprocals go both ways. So if cosecant is 1 over sine, then sine is 1 over cosecant. And so you can switch all of these around. Also, you should know that tangent of an angle is sine of that angle over cosine of that angle. So we'll use that fact to write tangents in terms of sine and cosine frequently. And we'll use this one, or these other guys, or these 2 guys, excuse me, to write secants and cosecants in terms of sine and cosine. And cotangent, since it's the reciprocal of tangent, it can be written as this one flipped, so it's cosine over sine. So I think these are called quotient identities, but these are the identities that come up pretty frequently. Now, I'm going to manipulate this a little bit further so I can use these identities to evaluate the antiderivative. Now, note to yourself that if you want, you could do the u sub and you'd get the right answer on this term. But it's simpler if you think of it like this. Cosine over sine is cotangent. And if I factor out a 1 over sine, well then this is equivalent to that. And you should check, multiply straight across, cosine times 1 is cosine, sine times sine is sine squared, so it works. These guys are equal. And we can actually multiply in any order we want, so I really should have switched them. I would have rather written them in the opposite order, and I'll tell you why, or you'll see why in just a second. Got cosecant squared here, I've got a rule for that. And then 1 over sine is cosecant, and cosine over sine is cotangent. And I have a rule for that. Now, if you see cotangent, cosecant, you can remember multiplication is commutative, so you could flip them yourself and that would be totally fine. But if I see the cosecant, cotangent, it's a little bit more obvious that it's a rule, probably rolls off your tongue a little bit better and you're used to hearing it that way and seeing it that way. So if I wrote it in the opposite order, like this would be helpful because I'd be more likely to remember my rule. If not, that's okay. You could always do the u sub up here, where u is sine of x. All right, so I think we're ready to apply our rules. The antiderivative of cosecant squared is negative cotangent. Then I have a minus there. The antiderivative of cosecant cotangent is negative cosecant. So it's negative times a negative is a positive. Cosecant of x plus c. And we might distribute, put the positive term first. All right, so that's multiplying by the conjugate. It's a lot, but this is the process, the procedure, the type of problem that you see when you multiply by the conjugate most of the time. It looks something like this, and it involves one of these three guys, usually. Or maybe something involving cosecant and cotangent, so that we could use that third Pythagorean identity. Then you multiply by and divide by the conjugate. Multiply the two conjugates together. Use the trig identity to simplify. Then we had to separate the numerator. Use reciprocal identities and quotient identities to simplify that. And then finally we're ready for a basic rule. So that's one where we do that. Here's another one. A little less obvious, but this is also multiplying by the conjugate. U sub doesn't work. Derivative of 1 plus cosine of x has a sign in it, and there's no sign out there. So we're going to have to multiply by the conjugate. Because that's under a radical, my conjugate needs to be under a radical as well. And remember, you can't just multiply by the conjugate, you also have to divide by it so that you're not changing the quantity, or excuse me, the expression that you are antidifferentiating. So we do that, multiply straight across. Square root of a times the square root of b is the square root of a times b. So I'm just putting it all under one radical. 1 plus cosine times 1 minus cosine is 1 minus cosine squared. All divided by the square root of 1 minus cosine. And this is sine squared, just like it was before. Now we're taking the square root of sine squared. Technically that's the absolute value of sine of x, but we're going to assume everything's nice. Either get plus or minus sine of x. So we're going to say, this is a special case when we get positive sine of x. You might say, I don't like doing that. And if you want, you can just say when sine of x is positive. It makes you feel better. So now I've written this way. The square root and the squaring function undo each other, and we get that as long as sine of x is positive. And we look at it like it's a new problem. Now what do? Do I have a basic rule for that? No, I don't have a quotient rule. Can I do u sub? Actually, I can. So we're going to let u equal 1 minus cosine of x and see if that'll work. This will work if the derivative of 1 minus cosine is up there somewhere, and it is. Derivative of 1 is 0. Derivative of negative cosine is a negative sign, so that's positive sign. Don't forget your dx. So this becomes 1 over the square root of u, so it's the square root of u, and the sine of x dx is du. So I want to rewrite it. Square root in the denominator becomes a negative 1/2 in the numerator. Then we add 1 to the exponent, divide by the new exponent. Dividing by 1/2 is multiplying by 2. Don't forget to back sub, put your u in. So that's our answer, but I need an answer in terms of x. It's going to be 2 times the square root of u plus c, where u was 1 minus cosine of x. So that's multiplying by the conjugate, guys. Variations on this, you might see 1 minus cosine of x under a radical. You might see 1 plus cosine, or 1 plus sine of x, or 1 minus sine of x. You might see secant plus tangent of x. Same is true over here. 1 plus cosine, 1 minus cosine, 1 plus sine, 1 minus sine, secant minus tangent, secant plus tangent, tangent minus secant, cosecant minus cotangent, like all of those. All of those could be potential expressions in the denominator. And when we multiply by the conjugate in the numerator and the denominator, what you'll see is that something will simplify. When we multiply these two guys together, we're going to get a rearranged version of one of these. It's going to be 1 plus or minus something, usually. Or secant squared minus tangent squared, that would be 1. Or cotangent squared minus cosecant squared, that'll be -1. You'll see when you do the problems. But you're going to see one of these guys, and that's your sign to multiply by the conjugate. These guys, where you multiplied by the conjugate from Calc 1, you're probably not going to multiply by the conjugate in those cases in this class. It's not necessary. We did this with limits in Calc 1, but we don't do this with integrals in Calc 2. Those expressions just don't show up as often in our integrands.